So I have prepared quite a bit of material to cover today, but I don't think I would cover everything in 2 hours. So I think what I'm going to do is I'm going to skip this part that I prepared on I think just the last part of chapter 2. I think it was chapter 2, section 7. So I'm going to share my OneNote later with everyone as well. So I'll probably link to it in the YouTube video description when I upload the recording to YouTube, which should probably be later tonight. And you guys will be able to kind of look at just a little bit that I wrote down for the stuff. But I thought what I would do is jump straight to the portion on vector spaces and subspaces first. And I thought we would begin with this topic. Okay. So real quick, a vector space, you can just think of a vector space as being a set of objects that can be added together and multiplied by scalars. So examples of vector spaces are Rn. Okay, so of course we can add any two vectors. Okay, and also multiply them by scalars. And then the other vector space that you've had a couple problems involving is the space of matrices. So of course we can add matrices together and we can multiply matrices by scalars. So that's also a vector space. In the past, they would sometimes do some stuff with spaces of functions, namely polynomial functions. I didn't see that this semester. So I'm going to guess that you guys maybe won't encounter that in your exam. So I'm not going to really touch on that much. And then here I gave like another example of a vector space. So if you take the set of all n by n diagonal matrices, that also happens to constitute a vector space as well. This example is kind of special because we know that the set of all n by n diagonal matrices, they are a subset of the space of all n by n matrices, which I'm denoting as Mn. So therefore, we would say that it's actually a subspace, okay? So the idea here is that a subspace is a vector space that's within another vector space. That's what a subspace would be. And to check if you have a subspace, there was two conditions that you needed to verify. So first is to be a subspace, your set has to be closed under addition. So what it means to be closed under addition is if you take any two elements of your set, their sum should also be in the set, okay? And then you also have to be closed under scalar multiplication to be a subspace. So what it means to be closed under scalar multiplication is if you take any element of your set, and then you take any scalar, that scalar multiple of your element has to be in your set again, okay? So I'm going to look at some examples of checking whether something is a subspace or not. And I'm going to start with this example here. So it is a fact about subspaces that they have to contain the zero vector. But you don't actually need to check that when you're checking with something as a subspace though, okay? The reason why you don't need to check the zero vector, just kind of real quick, is this second condition about the scalar multiplication. Since this is supposed to be true for any scalar, it's true in particular for the scalar 0. So as a consequence of the second condition, the 0 vector must always be inside of a subspace, okay? So usually this is useful to know to prove that something is not a subspace. So and we'll see an example of that later, but to show that something is not a subspace, if you recognize that the 0 element is not in the set, that's enough to say that's not a subspace, okay? Okay. All right, so then here I have this example here. So W is the set of vectors in R3, for which the y coordinate is twice the x coordinate and minus the z coordinate. So we want to check if W is going to be a subspace or not. So to check if W is a subspace, there were those two conditions again that we had to check. So I'm going to start by looking at the closure under addition. Okay. So to check if it's closed under addition, what we're going to do is we're going to take two vectors, W1 and W2. Okay. So these are two vectors in our set. So since these guys are in the set, that means that if W1 has coordinates x1, y1, but we know that the y coordinate has to be twice the x coordinate minus the z coordinate. And then let's say the z coordinate was z1, okay? So I'm going to write it out like that. That's W1. And then W2 needs to have the same kind of form to it, where the if x and z, if those coordinates are x2 and z2, the y coordinate has to be 2x2 minus z2, okay? So we have these two vectors in our set, and for closure under addition, we want to add them together, okay? So what I'm going to do is I'm going to add W1 plus W2. And of course, addition of vectors is just component-wise, so you're going to get x1 plus x2 for the x coordinate, 2x1 minus z1 plus 2x2 minus z2. So that's the y coordinate. And then the z coordinate is just z1 plus z2, okay? And that's just coming straight from adding w1 and w2. And now that we've added the two vectors together, we want to check whether their sum is inside of W, okay? So to check if the sum is inside W, we want to check if this vector here satisfies this condition to be inside of the set, okay? So to do that, here's the y coordinate of the sum. So we want to know, is this y coordinate equal to twice the x coordinate and then minus the z coordinate, right? So if I take the y coordinate that we have right now, notice that you can rewrite this as 2 times x1 plus x2 minus z1 plus z2. Okay. So this was the y coordinate of our vector. And we see that it is twice the x coordinate minus the z coordinate. Okay. So that means that the sum satisfies the same condition. And so we can conclude that W1 plus W2 is a vector inside of the set W, okay? So what this proves is for any two vectors in W, we've proven that their sum is also in W. And that means that W is closed under addition right now, okay? Now that's not enough to say that W is a subspace though, because to be a subspace, it also has to be closed under scalar multiplication. So we need to check that next. So checking scalar multiplication will be kind of similar. Let's continue working with the vector W1 that we had previously. And instead of adding W1 with another vector, what we're going to do here is we're going to multiply W1 by a scalar, okay? So I'll use C for the scalar. So C times W1 is going to be C times X1, and then C times the Y component. I think I'll go ahead and distribute the C to both terms. And then we have the Z component, just C Z1 out. Okay. All right, and then we want to kind of do the same thing. We want to check if this scalar multiple of W1, we want to check if this is in W or not, okay? So here's the X coordinate, here's the Y coordinate, and here's the Z coordinate. So we need to check if the Y coordinate, along with the X and Z coordinates, we want to see if they satisfy this equation again. So here's Y. So here you kind of already have it, I suppose. I guess because I already distributed the C. But yeah, you can see that the Y coordinate is already twice the X coordinate minus the Z coordinate, right? So that means this scalar multiple W1 is also inside of the set W. And so this would prove that W is also closed under scalar multiplication then. Okay. So then once you verify that your set is both closed under addition and also closed under scalar multiplication, that would mean that W is a subspace. Okay. In this case, it would be a subspace of R3, since it was a subset within R3. Okay. So then I'll maybe pause for a moment and I'll just ask if anyone has any questions about that. Okay. So I'll make a couple comments about this example before I move on to some other ones. So first, here in my example, I wrote the condition as like y equals 2x minus z. You could easily see the equation kind of rearranged though. So you might have seen the equation written as like 2x plus y minus z equals 0. Okay. And so when you're checking if you have a subset of R3 or just like Rn in general, anytime your condition looks like something like this, that means that it's going to be a subspace. So you should be able to prove that it is closed under addition and closed under scalar multiplication. If it doesn't look more or less something like that, then it's pretty much not going to be a subspace. Okay. So some ways that you might see this modified is if you had maybe the equation 2x plus y minus z equal to any number other than 0. So let's say if I change the condition to be equal to 1 now, then if that were the case, W would no longer be a subspace. Does anyone maybe see a quick reason why if I change the 0 to a 1 that it wouldn't be a subspace anymore? Yeah, that's true. If you change the 0 to a 1, it's not going to be closed under addition anymore. Okay. You can just make up an example to prove that. A simpler reasoning that I think you could give for this though is it also won't be closed under scalar multiplication. That's true. It also won't contain the 0 vector, so that's like another reasoning that you can use as well. Okay. So I know earlier when I was talking a little bit about the 0 vector, I mentioned that it's oftentimes useful to prove that something is not a subspace. So here, 0, 0, 0 would not be in this set if I changed it to equal 1. Because if you plug in 0 for x, y, and z, it's not equal to 1 anymore. So, okay. But yeah, you can also show that it's not closed under addition, and you could also show that it's not closed under scalar multiplication. You can do either of those, okay? To show that it's not a subspace, you only need to disprove one of those conditions though, okay? You don't need to like show that all of them are false. Just showing one of them is false is good enough. Okay, all right. If I change the equation so that it's not like something like here, if it's not just like numbers multiplying x, y, z and then being added or subtracted, it's not going to be a subspace either. So for example, for something like this here, where you have x, y, and z being multiplied with each other rather than being added and subtracted like we had earlier, something like this is not going to be a subspace. So you should be able to disprove one of the conditions of a subspace. I think this one, we could prove that it's not closed under addition, for instance. And you just need to give a counterexample to show that. So for instance, let's take the vector 1, 1, 0. Okay, so this would be a vector that's in W, because if you multiply the x, y, z components, it's equal to 0, okay? Here's another vector that's in W, because again, if you multiply the 3 components, it's 0. But when you add the 2 vectors together, you get 1, 1, 1, which is no longer in the set W, because now the components don't multiply to be 0. Okay. And so therefore, that means that W is not closed under addition. And that's why it would not be a subspace. And then I guess the condition that you see doesn't have to necessarily be in the form of an equation. So here I gave like an example where, okay, the condition is actually defined in terms of inequalities rather than an equation. If you see something like this, it's also not going to be a subspace, okay? For this one, the simplest example you could possibly give maybe is, again, this one does not contain the zero vector. Because we have that x, y, z have to be strictly positive, okay? But even if I changed it to all of them just greater than or equal to 0 instead, it still wouldn't be a subspace, although you'd have to give a different reasoning now. This one we can show that it's not closed under scalar multiplication. So take a vector whose components are non-negative. So this would be a vector in the set W then. But if you multiply by a negative scalar, this is no longer going to be in the set. And so that would mean that's not closed under scalar multiplication, okay? All right, any questions about that? Okay. Yeah, so really, the only time you have a subspace is if the condition looks something like this, where it's just x, y, z being added or subtracted, possibly multiplied by scalars, and then set equal to 0, okay? Note that they might rearrange the equation, so it also might look more like something like this, but if it's not something like this specifically, it shouldn't be a subspace, okay? All right, let's go down. Now, of course, you had a couple of examples involving vector spaces of matrices. So again, here I have an example of this time we're working with a subset of 2 by 2 matrices here. This time the condition that I have again takes the form of an equation. And again, I have it kind of in the form where it's like set equal to 0. So you can maybe guess that this is probably a subspace because it's similar to what we saw in the first example. But let's just kind of practice proving it again. So how would we maybe prove that this is a subspace? Again, you'll need to check closure under addition and scalar multiplication. So let's take two 2 by 2 matrices. We'll call them W1 and W2. And then notice I'm using like A1 and A2 and so forth for the entries. Sorry, that should be C2. And I want to assume that I'm working with two elements of our set. So I need to assume that these two matrices satisfy this equation, okay? So 2A1 minus B1 plus 3D1 is going to be 0, and same over here. Okay. Now what you need to do for check enclosure under addition is you need to add the two matrices together. So if we calculate W1 plus W2, so you're just going to get A1 plus A2, B1 plus B2, etc. All right, so then here you get like a new A, a new B, a new C, and a new D when you add them together. And then we want to check if the sum is inside of our set. So to do that, we need to check if the sum of the two will satisfy this equation, okay? So if I take 2 times the first entry minus the second entry B, which is B1 plus B2, and I do plus 3 times the last entry D, which is D1 plus D2. So I want to check, is this going to be equal to 0? And so to do that, what you can do with this is you can distribute everything and kind of rearrange the equation a little bit. So if you group together the A1 term, the B1 term, and the D1 term, and then you can group together the A2, B2, and D2 terms, okay? Then this first term in parentheses is going to be equal to 0 because we were assuming W1 was a matrix within our set, W. And likewise, the second term in parentheses is also 0 by this condition here, okay? So you can say this is like 0 plus 0, and therefore it's equal to 0 altogether. So we see that the sum of W1 and W2 also satisfies this condition. And so that means that it is within our set. So right now, the set W is closed under addition. Checking scalar multiplication will be similar. So what we can do is let's take the the matrix W1 from before. And let's say if I multiply it by some scalar, this time I'll use K for the scalar since I'm already using C inside the matrix. So if you multiply by K, you're going to get KA1, KB1, and so forth. And then again, checking if it's inside of the set W now. So we need to take the new A entry, multiply it by 2. We need to minus the new B, which is KB1. We're going to add 3 times the new D, which is KD1. And we want to check whether this is going to be equal to 0 or not. So in here, what we can do is we can pull the k out of everything. If you factor it out, you'll be left with 2a1 minus b1 plus 3d1. And that expression in the parentheses, again, that's going to be equal to 0. So therefore, this is k times 0, and so it's equal to 0 altogether. Okay. So we see that k times w1 satisfies the same condition up here. So therefore, it's inside the set w, which means that w is also closed under scalar multiplication. So then once you prove that it's closed under addition and scalar multiplication, you can conclude that you have a subspace. In this case, it would be a subspace of the space of 2 by 2 matrices, which I denote as M with a subscript of 2, okay? And I think your professors do that as well. All right, any questions about that? Okay. Now with matrices, matrices are maybe like a little bit more versatile for your professors in the sense that they might define W like not in terms of an equation, like how I did up here. So like here's another example where we're just looking at W being the set of all n by n symmetric matrices. Okay. So if we were to check if this is a subspace or not, it turns out that this will be a subspace, okay? So if I were to give a quick sketch of a proof of this, the key that you have to use here is that, remember that for a matrix to be symmetric, that is equivalent to saying that A should be equal to its own transpose, okay? So you can use that property to check if it's going to be closed under addition and scalar multiplication. So I'll kind of quickly work through those, okay? So let's suppose we have two symmetric matrices. And we'll call them A and B. Because they're symmetric, that means A and B are going to be equal to their own transposes. We want to check if their sum is going to be symmetric. So if we add A and B to get A plus B, and if we try to transpose the sum, one of the properties of transpose is that you can, with an expression like this, you can distribute the transpose to each term of the summation, so that this is the same as A transpose plus B transpose. And since A and B are assumed to be symmetric right now, A transpose is equal to A and B transpose is equal to B. So you can say that this is equal to A plus B, okay? Okay, so since we have the A plus B transpose, we just showed that it's equal to itself, A plus B. So that means that when you take two symmetric matrices and you add them together, the sum is also symmetric. And so that proves that this set of symmetric matrices is going to be closed under addition then. And then similar, if you wanted to check the closure under scalar multiplication, again, assuming that you have a symmetric matrix A, what we can do is multiply it by an arbitrary scalar. So again, here I'll use C for the scalar. So if we look at C times A, and we look at the transpose of it, there is a property of transpose that you can pull the scalar outside of the parentheses. So this is just C times A transpose now. And then again, we're working with a symmetric matrix here. So A transpose will be equal to A. So this is just C times A. Okay. So we've proven that the transpose of CA is equal to itself. So that means that CA is symmetric, meaning it would be inside of the set of symmetric matrices still. So here we're seeing that if you take a symmetric matrix and you multiply it by a scalar, the result is still going to be a symmetric matrix. So that proves that it's closed under scalar multiplication. And therefore it would be a subspace. In this case, it would be the subspace of the space of all n by n matrices. So a subspace of m n. Okay. So that one's maybe like looks a little bit more abstract because it's not as explicit as the ones before, where you were working with matrices of a specific size. Okay. And I don't think I'll spend much time on this one, but the set of all n by n upper triangular matrices, it's also going to be a subspace. So super quick reasoning, basically, it's closed under addition because if you add two upper triangular matrices, the result is still upper triangular. I'm just gonna shorthand triangular with a triangle. Yeah, so the sum of upper triangular matrices is still upper triangular. So that means that it's closed under addition. Likewise, if you take an upper triangular matrix and you multiply it by a scalar, can you guys still hear me? Okay. The lights just went out, so I don't know if that means something's going on with the power, but it looks like I still have internet connection though. So I'll go ahead and continue, all right? So hopefully the power isn't going to affect this. Yeah, I know, yeah. Yeah, so a scalar multiple of upper triangular matrix of an upper triangular matrix is still upper triangular. So that proves that it's closed under a scalar multiplication, okay? All right. And then also just to wrap things up real quick, set of all n by n invertible matrices is not a subspace. So you can give a very quick reasoning for that one. It's not going to be closed under addition. So you could give an example of that. It also just doesn't contain the zero matrix though. Because the zero matrix is not invertible. So and then if you look at the setup all n by n non-invertible matrices, so matrices that are not invertible, that's also not a subspace. So you can give an example showing that it's not. In this case, you can show that it's not going to be closed under addition. So for instance, you can take a matrix that looks like the identity, except let's say that the very last entry is 0. Okay. So this matrix would have a row of zeros at the bottom, and so that would make it not invertible. And then you could take another diagonal matrix, this time 0 across, except the last entry is a 1. So both of these matrices are not invertible. So both are singular, if you will. But their sum is the identity matrix, which is invertible. So when you add two singular matrices, the sum is not necessarily singular anymore. So that it's not closed under addition. And so it would not be a subspace, okay? All right. So I guess let's go on to another topic. Okay. So I guess I figured I should talk a little bit about linear independence, span, basis, and dimension. So going over the definitions and maybe trying to do a couple of quick examples. Okay. So if you have a vector space, okay, and then let's say you have some vectors v1 through vk inside the vector space V. So the definition of linear independence, I've written it out here. So vectors v1 through vk are linearly independent if the only solution to this equation, where it's equal to 0 on the right-hand side, is what they call the trivial solution, where all of the coefficients are equal to 0, okay? So that's the only solution to the equation. They are linearly independent. The span of a collection of vectors is the set of all of their linear combinations, okay? That's what the span of a collection of vectors is. And the span of any collection of vectors is always a subspace of the vector space that they were residing in, okay? A basis is a set of vectors that spans your space and is also linearly independent. And then lastly, the dimension of a vector space is defined to be the number of vectors in any basis of that space, okay? So this is a very quick rundown of some of the definitions. And then let's look at this example that I have here right now. So this is kind of like a typical question that one might be asked in a linear algebra class. that involves like these notions of linear independence and span. So we're given 3 vectors in R3, and we want to show that they form a basis, okay? So to do this, there's a couple of ways you can do it. So one thing you can do is, of course, to show that you have a basis, you can show that your vectors are linearly independent, and also show that they span all of R3 in this case, okay? So to check for the linear independence, if you form a linear combination of the 3 vectors, so C1v1 plus C2v2 plus C3v3, we need to set this equal to 0. And then we need to check what are the solutions to this equation, okay? So if the only solution is that C1, C2, C3 are 0, that will prove that they are independent. So to solve for C1, C2, and C3, what you can do is, set up your usual augmented matrix and do the elimination, okay? And so that shouldn't be too long, so I'll do the row operations real quick. So I want to do row 2 plus row 1 and row 3 minus row 1. Let's work out the rest of the matrix. That's 1 and 3, 2 and -2. And if we were to just do like one more row operation, row 3 minus 2, row 2, that would put it into the upper triangular form. And from here, if you were to write out the corresponding system of equations, you guys can see that C3 will be 0. You can back substitute, and you'll find that C1 and C2 are also 0. So because that was the only solution that we found, that means that these 3 vectors are linearly independent right now, okay? Now, to check that we have a basis, a basis also needs to span the whole space, okay? But rather than checking that they span, there is another argument that you can often make in this type of question, which depends on the knowing the dimension of your space, okay? So we know that R3 is a 3-dimensional space. So if you have a 3-dimensional space, then any 3 linearly independent vectors will have to span the space. And so usually using this sort of dimensionality argument, it's going to be quicker than checking span. And you can kind of generalize this to any dimension. So it might be useful to know that just in general, if the dimension of the space is known to be some number n, okay? And then if you have n linearly independent vectors, then those vectors are automatically going to span the space and therefore be a basis for it, okay? So oftentimes for these types of questions, you can get away with just checking the linear independence, because once you have linear independence proven, if you have the same number of vectors as the dimension of the space, that will be enough to conclude that you have a basis, okay? So in the event that maybe you have a space where you didn't know the dimension ahead of time, so if like you weren't too sure about it, then you would want to maybe check the expanded space instead, okay? So I thought I would just try to do like one more example of this type. So here I have an example, this time with matrices. And we're looking to see if these three matrices that we have form a basis for the space of all, 2x2 symmetric matrices is what I meant to say there. Let me fix the example. All right, everyone, sorry for that. You can kind of guess what happened, yeah. So internet went out. I'm using my personal hotspot. So let's see here. Let me reshare my OneNote. All right, so let's try to continue. So here we have 3 symmetric matrices. We want to check if they form a basis for the space of all 2x2 symmetric matrices. So if I check for linear independence first, so here you would set up the equation C1 V1 plus C2 times V2 plus C3 times V3 and set it equal to 0. Because for linear independence, that's the equation in the definition. And remember, what we want to do is check if C1, C2, C3 must be equal to 0, okay? All right, so this time what you can do is if you convert this to a system of equations by adding the components, looking at just the first entry right now, you're going to get like 1C1 plus 1C2 plus 0C3 has to equal 0. So you get one equation from that. And you can write out the rest of the equations, which I'll do real quick. You're going to get 0C1 plus 1C2 plus 1C3 is 0. You're going to get the same equation if you use this third entry because the matrices were symmetric. So you don't need to write that one down. But the last equation was going to be 0C1 plus 0C2 plus 1C3 is 0. Okay, so here, fortunately, some pretty simple numbers. So we don't need to do any elimination to solve. We can actually just right away see that C3 is 0. And then back substituting will give you C2 is 0. And then you see that C1 is also 0. But if it were more complicated, you would go ahead and set up an augmented matrix and do the elimination to solve for C1, C2, and C3. My audio is cutting out. Oh, I see. My connection is maybe not super good. Yes, yeah, hopefully. Oh, yeah. I was using, so I'm writing on my laptop, which functions as a tablet as well. And I was using my work desktop computer to monitor e-learning. But since there's no internet here, my desktop isn't connected anymore. So I need to actually switch back and forth between e-learning and OneNote to check the chat now. And whenever I switch to e-learning, you're going to see that black screen for a little bit. Yeah, okay. So every time you see a black screen, it just means that I'm checking the chat, basically. All right. Okay, so yeah, let's see if, I don't know, I tried moving my phone closer to my laptop. I don't know if that will improve the connection, but we'll see. So here, this proves that the three matrices that we have are linearly independent. And here, we're maybe not as familiar with 2x2 symmetric matrices. So we maybe don't know what the dimension of the space is. So if you have such, you won't be able to apply this to conclude that you have a basis. So therefore, what we might do is we might actually just try to show this will span instead. Okay? Okay. So I'll try to say that again. Hopefully it will come out. But, if we're familiar with the space 2x2 symmetric matrices, then we maybe don't know what its dimension is. If you don't know the dimension of your space, you won't be able to apply this fact to solving the problem. So in the event that you don't know the dimension of your space, then you're going to need to show that your vectors will span the space in order to show that they are a basis as well, okay? So we've proven they're linearly independent. Now we want to show that they also span the space, okay? So let's check how we would do that, because I guess this may be good to see an example of how you would. So to show that these three matrices span the space, what that means is if we take any 2x2 symmetric matrix, okay, and here notice that since I am working with symmetric matrices, that's why I made these two entries the same. So we want to see if any 2x2 symmetric matrix can be expressed as some linear combination of our given vectors, or matrices in this case. So what you do for standard is rather than this equal to 0, as you do for linear independence, you set it equal to an arbitrary element of the space. So in this case, we're working 2x2 symmetric matrices, set equal to an arbitrary 2x2 symmetric matrix. Now, again, we can convert this into a system of we'll have the same left-hand side as before, but the right-hand side, rather than being 0, now we have A, B, and C on the right-hand side, okay? Now, in this case, I guess maybe this equation was maybe too simple, but we already have a solution for C, and you can back substitute to solve for C2. So it's B minus C3. And then you can back substitute into the first equation, and therefore you can solve for C1. It's A minus C2, okay? So since we found a solution, so what this tells us is every 2x2 symmetric matrix can be expressed as a linear combination of V1, V2, and V3. And so that would prove that V1, V2, and V3 span the whole space, okay? And then because they are linearly independent and also span the whole space, that would prove that they were a basis for the space, okay? Okay. And then let me just make some general comments about like things you should be looking out for when you're checking if a set of objects is linearly independent or spanning your space. So just real quick, when you're checking for linear independence, if you have something that's more complicated than this, you may need to set up an augmented matrix and do elimination to actually solve system equations. Now, when you're solving the system of equations, there's going to be two possibilities. So either this is your only solution, and that would mean that they are linearly independent. If this is not the only solution, then that means you have infinitely many solutions instead. So seeing infinitely many solutions would be the indication that they are not linearly independent. You can see that. And then to have infinitely many solutions, remember that means that you have at least one free variable or at least one free column. If you're not too familiar with that, we'll talk more about it. But you have at least one free column, meaning at least one column without a pivot. So that's kind of what you can look out for to know that they're not independent. So then therefore to be linearly independent, that means if you were doing elimination to solve the system of equations, what you'd want to see to be linearly independent is a pivot in every column, because that would ensure that you have a unique solution. So that's just kind of quick notes on what you should be looking out for, perhaps. For span, what you want to be looking out for is, so to span, that means that a solution needs to always exist. Okay. And that's going to be no matter what you have on the right-hand side, because the right-hand side is going to be arbitrary when you're checking for span. So in order for a solution to always exist, for the solution to always exist, that means that you won't have any rows of zeros when you're doing your elimination. Because remember that if you do get a row of zeros, that's an indication that you're going to have no solution whenever the right-hand side is non-zero. So therefore, to span, to always have a solution, you need to make sure that you have no rows of zeros for that. So if you were doing elimination to check that they span the space, then try to check that you have no rows of zeros. If that's the case, then you'll know that they span, okay? Okay, so maybe any questions about that? before I talk about more stuff? Okay. So next we'll talk about Columnspace a little bit. So for any m by n matrix, the Columnspace of A, it is the set of all linear combinations of the columns of A. And remember, that's just the span of the columns of A as well. So those are the same thing. And then the column space of A, it also turns out to be the set of all vectors B, for which the equation AX equals B has a solution. So that last one, you might not see the connection immediately with the other two definitions. But just real quick, why the last one be true? Remember that when you do matrix vector multiplication, and I'm just going to illustrate with a 2x2 matrix. Remember that when you do A times X, that results in this linear combination of the columns of A. So when we're saying that B is equal to A times X, we are saying that B is a linear combination of the columns of A. And so that's where this definition of Columnspace comes from, okay? All right. The Columnspace of A is always a subspace because its span of any collection of vectors is going to be a subspace. And specifically, the Columnspace is always a subspace of Rm if A is a size m by n matrix, okay? And if that's a little confusing, you can just think of a quick example to see why that would be the case. So if your matrix is like example 2x3, your columns are going to be vectors in R2 because each column has two components to it. Okay. So that's why the column space would be in R2 in this example, and more generally be in Rn, because that's how many components each column would have. Okay, that's just kind of real quick. So here, if we look at this example real quick, so I kind of had like 4 different questions written out. So the first question was, is that vector B323 a linear combination of these 3? Second question is B in the span of those vectors? Third question is B in the column of this matrix? And notice that the columns of this matrix are the 3 vectors in the previous questions. And then the last question is, does this equation AX equals B have a solution? And so what I kind of wanted to point out is that these 4 questions are actually all the same question, okay? So the same question can be worded in like many different ways, as you can kind of tell. But these are all the same because all of them are just checking to see is B a linear combination of these 3 vectors that comprise the columns of A, okay? So to answer all of these questions, you just need to try to solve this equation. So If you wanted to solve it, you would just do the usual elimination to see if a solution exists. So I'll just do that real quick. We'll start with row 3 plus 2 row 1. It's going to be 0, 1, 8, and 9. And if we just do one more row operation, that will put it into the upper triangular form. Okay. And here we see that you would be able to solve this equation by back. So a solution does exist. So because a solution exists, so the answer to the last question is yes, equation does have a solution. And so therefore the answer to the previous 3 questions would also be yes as well, okay? So just kind of try to keep in mind the different definitions of column space, just because, maybe if you're not familiar with all the definitions, that you could see a question worded in a way that you're unfamiliar with, but it was really a question that you knew how to answer all along, okay? Okay. Questions about that? Okay. Let's see here. Okay. So just take a look at, or a look at another example, specifically about column space. So I think you had questions on your homework assignment that were of this type, where it was something of the effect of find a condition on a vector B for it to be in the column space of some matrix. And so the way that I kind of figured one would go about this type of question. So remember that to be in the column space of the matrix, let's call the matrix A. Then remember that B is in the column space if and only if the equation AX equals B has a solution. So therefore, the question is the same as asking what conditions on B are needed for there to be a solution to the equation AX equals B. And to figure that out, what you should do is just start trying to solve the equation. So I'm going to take A, I'm going to augment it with B. And then we're just going to start trying to solve, and we're going to see what happens. So I'm going to do row 2 plus row 1, and row 3 minus 2 row 1, okay? Okay. So I did those two row operations, and then to get it to upper triangular form, we would do one more operation. Row 3 minus 3, row 2 this time. Now notice that we get this row of zeros, and then on the right, we have row 3 minus 3 of row 2, which altogether leaves us with 5b1 minus 3b2 plus b3. Okay? So then for a solution to this system of equations to exist, we would need the right-hand side, this entry in particular, to be non-zero. Or no, to be equal to 0 rather, for there to be a solution. Because if it's not 0, you'd have 0 equals something non-zero, and that would mean no solution. So we need this to be equal to 0, okay? So then this equation would be a condition on the vector b for it to be in the column space. Okay. And so then that would be like the answer to that question then. So any questions about it? Okay. So let's talk a little bit about null space next. Should we provide a particular solution? No, so for a question like that one, this one here, no, I don't think you would need to provide a solution at all. They just wanted the condition, and that equation that you get at the end, that would be the condition that they need, okay? Okay. So talking about null space a little bit, remember that the null space of a matrix is the set of solutions to the equation ax equals 0. And then I thought I would talk about the complete solution to ax equals b as well while I'm at this. So when you have an equation ax equals b, and if it has infinitely many solutions, then it turns out that the solutions will have a particular form to them, x equals xp plus xn. So here in this kind of equation, xp is going to be one particular solution to the equation. And then xn is going to represent the general solution to ax equals 0. So the n kind of stands for null space because this would be an element of the null space since ax is equal to 0, okay? And if you were asked to find the complete solution to an equation ax equals b, what you want to do is start by reducing to row echelon form at least Personally, I tend to reduce to reduce row echelon form for these types of problems, just because I prefer it that way, but it's not necessary. Just reducing to row echelon form is fine as well. And here, what I've done is I've gone ahead and I've set up A, augmented with B, and I thought it would be good if I saved some time by just doing all the row operations ahead of time, okay? So here's the final results that I got. Reducing it all the way to reduced row echelon form is what I did. And then I thought I would reduce from here and to see how we would finish the question. I'm going to go and circle the three pivots that we had in this problem. And then once you get to a row echelon form, you can go ahead and convert everything back to a system of equations. So in my first row, that gives me the equation like x1 minus x3 minus x5 equals 1 on the right-hand side. We've got like a x2 plus x3 minus x5 is 0. And then we have x4 plus x5 equals 1 from the third row, okay? So I know that people will do this part in different ways, so I'm just going to show you guys the way that I always handle this. So we're going to have infinitely many solutions, so we're going to have some free variables. In this case, we can choose x3 and x5 to be free variables because the third and the fifth columns, those are the ones without pivots. And you can always choose your free variables to be those variables that correspond to the columns without the pivots, okay? So what I personally do is I assign a parameter to each of the free variables. So I'll use maybe S and, well, let's not use S, let's use R and T. Okay. And then what I'm gonna do is I'm gonna solve for the variables I and T. So if x5 is T, I can substitute that into this equation. And that's gonna give me x4 is 1 minus T. In this equation, I can substitute x5 is T and x3 is R and solve for x2. So it's going to be minus R and plus T. And then again, plug in R and T for x3 and x5. Move them over to the other side. So we're going to get x1 is 1 plus R plus T, okay? And then I'm going to rewrite that now in a sort of vector format. So I'm going to put all the x's into a. And what I'm going to do for the right-hand side is I'm going to write it in a particular way. So normally the way that I'm going to do this is we have x1 is 1 plus 1r plus 1t. So I'm going to fill in 1, 1, 1 like that. And so right now that gives me x1 is 1 plus 1r, whoops, plus 1t. X2 is 0 minus 1r plus 1t. X3 is just 1r. X4 is 1 plus 0 r's and minus 1t. And finally, X5 is just 1t, okay? So does everyone kind of see how I got that? Okay. So then once you write it in this form, this part here with the r and the t in them, this is actually going to be the general solution to your ax equals 0 equation. So this part is actually representing your xn part of the complete solution. And then this vector here, this is going to be your particular solution, xp. Okay. So here what's happening is you get a solution for each possible value of r and t. So really r and t can be like any real numbers. So in the partial where r and t are equal to 0, you would get this vector as a particular solution. So that's your particular solution. And then again, this part here with the parameters in it, that's going to be your xn. So when you're looking for the complete solution to a system of equations, you don't necessarily need to do anything too special. Just solve your equation the usual way. And it should work out that your solution will just naturally come in the form of a particular solution plus xn, depending like what's in your null space. Okay. Okay, so I guess I'll go ahead and move on. Okay, so talking about the fundamental subspaces of a matrix. So there's 4 of them. We've looked at the column space and the null space. The other 2 are the row space. And the row space is just the, okay. So the row space is just the column space of A transpose. So the idea of that is the columns of A transpose are the rows of A. Then we also have the left null space, which is the null space of A transpose, okay? And typical question that you might get for these guys is to find a basis for each of the fundamental subspaces. So to do that, you want to reduce your matrix to at least a row echelon form. Once you do that, you can identify which columns have the pivots in them. And if you take those pivot columns, but take them from the original matrix rather than the reduced matrix, that's going to give you a basis for the column space of A, okay? To get a basis for the row space, take the rows with the pivots in them. You can actually take these from the reduced matrix rather than the original matrix. And it is a little bit safer to pull them from the reduced matrix than the original matrix. So if I had to choose, if I were to recommend one of those to you, I would recommend pulling your basis for the row space from your reduced matrix, okay? So those guys will be a basis for the row space. To get a basis for the null space, that's your special solutions. If you don't know what special solutions are, we'll see that in the example. The null space is one that's a little bit harder to find a basis for. But what you can do to get a basis for the left null space is take your basis for the column space of A, put those basis vectors into a new matrix, but this time as rows because you need to transpose them. So we call that new the null space of B left of A. So you just need to find the null space of that new matrix, okay? So I'll start with an example, okay? So here we want to find a basis for each of the four fundamental subspaces. Again, to save some time, I went ahead and reduced this, and I reduced it all the way to the reduced row echelon form, okay? I've got the pivots circled already. So at this point, to get a basis for the column space of A, I see that the pivots are in the first, the second, and the fourth columns. So I want to take the first, second, and fourth columns, but in the original matrix A. And then those vectors are going to give me a basis for the column space, okay? To get a basis for the row space, we can take the basis from the reduced matrix at the end. And you just want to take the rows with the pivots in them. So basically all the non-zero rows. So those three vectors are going to give you a basis for the row space. Okay. And you'll notice that I'm writing these rows as columns in the basis. So one reason for understanding why you would want to write them as columns is because if you'll remember, the row space is actually the column space of the transpose. It's what it's supposed to be. So therefore, you're actually looking at columns of each transpose. So you should write them as like columns actual rather than rows. So that's kind of one reason why you should be doing that. Now, some of you will take the original rows to get a basis for the row space. And that is okay. But there's maybe one thing that you should be aware of if you are going to do that, which is when you are doing your row operations, reduce your matrix. If you did a row swap, so for example, I didn't do any row swaps here. As an example, let's suppose at some point I actually did row 3 swap with row 4, okay? That means that this row 3 at the end is actually your row 4 from the original since you swapped, okay? So if I had done the row 3 swap with row 4 at some point, and then I wanted to get a basis for the row space using the original matrix, I would actually need to pull row 1, row 2, and row 4 rather than row 1, row 2, and row 3, okay? So if you do insist on getting your basis from the original for row space, be aware if you did any row operations, But honestly, it's just easier to just always pull it from your reduced matrix, so you don't have to worry about that. So that's why I recommend to just pull it from the reduced matrix to get your basis for the row space. Okay. To get a basis for the null space, what you need to do is, let's see. Yeah, I'm going to be posting here, and I'll send everyone the link to it once I have it uploaded. Okay. So then for the null space, what we're going to do is from the reduced row echelon form. Okay. Each row is going to give us an equation. So the first row is going to give us 1x1 plus x3 minus x5. And for null space, the right-hand side is all zeros. So we're going to get this system of equations to solve for the null space. And then here we can do this the same way that I kind of did in the last problem with the complete solution. X3 and X5, we can make those the free variables. Because the third and the fifth columns did not have a pivot when we had reduced at the end. And again, I just do it the way that I personally do it. So I make X3 some parameter R, and I'll make X5 T. I'll solve for X4, X2, and X1. Okay. So different people do it different ways. This is just, I have a personal preference of doing it. So X5 is T. So if I were to sub that into here, you will get X4 is negative T. If X5 is T and X3 is R, move everything over. X2 is R plus 2T. And likewise, X3 is going to, sorry, X1 is going to be negative R and plus T once you move everything over. Okay. And to get the basis for the null space, you can pull the coefficients of each of your parameters. So if I pull all the coefficients of R, we're going to have negative 1, 1, 1, 0, 0. So those are all the coefficients of R. And then you pull all the coefficients of T, which are 1, 2, 0, minus 1, and 1. And that's going to be the basis of the space, okay? And then lastly, to get a basis for the left null space, previously that's always the one that's a little bit harder to do because you can't get the null space from the work that we've done over here, okay? But what you can do for the left null space is take the basis for the column space that you found previously, put those into a new matrix as rows. And then you're going to want to find the null space of this matrix here, okay? So I'll do that real quick. Row 3 minus 2 row 1. Next, I'll do row 3 minus 3 row 2. And I'll go ahead and do row 1 plus row 2 as well, just to eliminate everything above and below the next pivot, okay? And here, so this was the second pivot. The 1 here was the first pivot, okay? So eliminating both above and below is what you'd want to be doing if you wanted to get all the way to the reduced row echelon form. But you can just do a regular row echelon form as well. I just row echelon form when I'm doing this. Okay. So here we're adding row 2 to row 1. And then row 3 minus 3 row 2, I think that's a 1 again. That's going to be -7 though. Okay. All right. And I'll go ahead and eliminate everything above the last pivot. So here's the dirt. Okay. So if I wanted to get reduced row echelon form, I will do row 2 plus row 1. Sorry, not row 1, row 3, rather, the pivot row. And I'll also do row 1 plus row 3, and that will get rid of those negative ones. And I'm adding -7 to everything else, so I'm going to get that. Now that I've reduced all the way, I would write out the corresponding system of equations from this. Since we're looking for the null space, again, you're going to be setting it equal to 0. So if I set x4, our free variable, equal to, let's do t, we'll get x3 is 7t, x2 is 6t, x1 is 4t, and so we can then get a basis for the left null space from that. So it looks like there's only one vector in the basis for the left null space. And taking the coefficients of t, we have 4, 6, 7, and 1, okay? All right, so any questions about that? Okay, so I'll go a little bit longer. I know it's 6:30 now. Of course, you can leave it any time, but I'll go a little bit longer just because I'm a little bit late, and I know there's also that interruption in the middle. So, okay. Real quick for how we got the Columnspace. So basically, you row reduce your matrix, and you look for which columns had the pivots in them. So in this example, it was the first, the second, and the fourth columns that had the pivots. So you take the first and second and fourth columns, but from the original matrix, and that's going to give you the basis for the column space, okay? Okay. So talking a little bit more about the fundamental subspaces. So there was the notion of the rank of a matrix. So remember that the rank of A is equal to the number of pivots in A. And it also happens to be equal to the dimension of the column space as well as the dimension of the row space. Okay. And that's because you get one basis vector for each of these with each pivot column and each pivot row. Okay. So that's the rank of A. And there were these orthogonality relations between some of them. So and the null space were orthogonal complements of each other. So this means that every vector in the row space is orthogonal or perpendicular to every vector in the null space. And also their dimensions of the row space and null space always add up to be equal to n, okay? And similarly, the column space and the left null space, those guys are also orthogonal complements. So not only are they orthogonal to each other, but their dimensions are always going to add up to be equal to n as well, okay? And here, this is like a super quick question. I don't know if it's necessarily a question that you would see on your exam, but I think it's maybe just kind of a good one to see to kind of tie some of these facts together. So here I'm saying a 2-3 matrix with a rank of 2. So with that information, we can actually say a lot about what the fundamental subspaces of A are going to look like, okay? So with this information, what can we say? So for starters, we know the dimension of the column space and the row space are both going to be equal to 2, because that was the rank of the matrix. We can also figure out the dimensions of the null space and the left null space using these equations here, okay? So the dimension of the row space, which is equal to 2, plus the dimension of the null space, this has to be equal to 3, because 3 is the number of columns of our matrix, so n would be 3. So therefore, we can say that the dimension of the null space is equal to 1. And similarly, you can solve for the dimension of the left null space as well, using this equation here. Because we know the dimension of the column space is also 2. So if we do that plus the left space, that has to be equal to m, the number of rows in A, and here A is 2 by 3. So n would be 2. So this tells us that the dimension of the left null space is actually equal to 0 then, okay? Okay. So we have all the dimensions of the subspaces. Now let's see, so the row space and the null space, these guys are always subspaces of Rn. And the column space and the left null space, these guys are always subspaces of Rm instead. So looking at what we have here, so the dimension of the row space is 2, and a subspace of R3. So being a two-dimensional subspace, that means that the row space of A is going to be a plane if it's two-dimensional. So it's a plane in R3, and because it's a subspace, it has to contain the 0 vector. So that means the row space of A, that would be a plane that passes through the origin. And R3. So that's what we can see about the row space. The null space we know is one-dimensional. So it's going to be a one-dimensional subspace of R3. And we also know that it's going to be orthogonal to the null space as well. That means that it's be a line in R3. A line because it is one-dimensional, okay? Again, it passes through the origin because it's a subspace, so it has to contain the 0 vector. And the line is going to be orthogonal to the row space. Okay. If we focus on the column space and the left null space, those guys are going to be subspaces of R2 in this example. But the column space itself is two-dimensional. So if it's a two-dimensional subspace of R2, that means that the column space of A is just R2 itself, because R2 is already two-dimensional. So the only two-dimensional subspace of it would be itself. And then lastly, looking at the left null space, dimension of the left null space was 0. So that just means that the null space or the left null space is trivial, meaning it consists only of the 0 vector. Okay? So it's just the origin, just a point. And it's in R2 because it's a subspace of R2. So that's why we did 2 zeros for the origin there. Okay? So this is kind of a small example. Again, I don't necessarily think that's maybe a question you would see on your exam, but I thought it was just a kind of a good question to see how everything relates, okay? Okay, and I think I'll go ahead and jump to projection of least squares as the last topic. And for the stuff that I didn't go over, again, I am going to share my OneNote later with everyone, so you'll be able to see like anything that I didn't cover in my OneNote, okay? So for projection and least squares, and you guys, I think the exam does not actually go up to least squares. It really only goes up to talking about projections, okay? But I find that to understand projection, it's good to talk a little bit about least squares anyways. So the general setup is we have a subspace S of Rn, and in the picture I'm representing S as if it were a plane, okay? But it doesn't have to be two-dimensional, it could be any dimension. We have a vector B, which is not in S, so that's represented by B sticking out of the plane. So if we were to like drop a perpendicular down from B onto S, this vector here that you get, so it kind of looks like the shadow of B along S, if you will. That's called the projection vector. It's the projection of B onto the subspace S. And some people will call this the orthogonal projection of B onto S. But in this class, we only talk about orthogonal projections, so it's not important to emphasize the orthogonal part. And what's special about this projection vector is that the projection vector, it's the vector in S that is closest to the vector B, okay? Now this vector here that I've drawn in red, in your textbook, I think they denote it with E and they call it the error vector. But this error vector is really just B minus its projection P, okay? Because that's the difference between the two vectors there. And the error vector is orthogonal to the space S, okay? So that's kind of the general picture of what projection looks like, what you're actually doing. And the reason why we're talking about projections in this class is they help us deal with the case where the equation ax equals b has no solution, okay? So we know how to handle the case where ax equals b has a unique solution. That's just the elimination and back substitution stuff that you did in the first part of the semester. We know how to deal with a case where it has infinitely many solutions now as well, because you just got your free variables and whatnot. So in the case where we have no solution, we can use projections to do something about that. So if the equation ax equals b has no solution, that means that b is not going to be in the column space of A. Because remember, we talked about it earlier, but to be in the column space, that's equivalent to saying that there is a solution to this equation. So therefore, no solution means not in the column space. So you get this kind of picture here, where now we have the column space of A. B is not in the column space. But what we can do is project B onto the column space of A. And because the projection vector is in the column space, that means that the equation ax equals p will have a solution, okay? And since p is the vector in the column space that is closest to the vector b, then in some sense, that means that solving the equation ax equals p is the closest that we can get to solving the original equation ax equals b, okay? So a solution to the equation ax equals p is called a least squares solution to the original equation. And I think your book denotes the least squares solution by x with a hat on top. And I think your professors have used that notation a little bit already. that's what the x hat refers to. It's the least squares solution. Okay. So the idea is that the least squares solution is kind of the next best thing available to an actual solution, which we know does not exist to the original equation. Okay. And to solve for the least squares solution, you guys can take a look at what I've written here. But maybe to save time, to solve for the least squares solution, you can actually solve it by solving this equation here instead. Okay. So the least squares solution will satisfy this equation. So you typically use this equation to solve for the least squares solution. And if A transpose A, if that matrix is invertible, you can multiply both sides by the inverse, and you get the formula here for the least squares solution. And then since A times x hat is your projection vector, if I take this and I plug it into here for x hat, you get this equation now. Okay. So all this stuff will multiply with the vector b to get the projection of b onto the column space of A. And then this stuff here, if you group that all into a matrix capital P, that capital P is your projection matrix. Okay. And so here I've kind of summarized a little bit of what we have there. So if you want to project a vector onto a subspace, first you need a basis for that space. Put the basis vectors into a matrix as columns. Once you have that matrix, you can calculate the projection matrix. And then you take that projection matrix and you multiply it with B, and that will calculate the projection of B onto S, okay? You can also calculate the projection vector without getting the projection matrix. The way that you would do that is you would find a least squares solution by solving this equation using elimination. And then once you solve for x hat, you can also just do A times x hat to get the projection vector, okay? So I don't tend to use method 2 that often, but that is like another way you could calculate the projection vector without actually calculating the inverse of A transpose A, okay? There's a couple of special cases of this, which is if S is a one-dimensional subspace, in other words, if S is a line, and let's say it's a line spanned by a vector A, then this formula for the projection matrix simplifies to be this. As A becomes a scalar, so if it's raised to a power -1. Also, this came up in your last homework assignment 9, I guess. But if you have orthogonal vectors, you can also calculate the projection vector as a linear combination of those orthogonal vectors using this formula here, okay? Make a quick comment that whenever you have a vector transpose times another vector, this is equivalent to just doing the dot product of the two vectors. So sometimes you'll see these formulas written as dot products in the numerator and the denominator, okay? And I'm gonna try to wrap up by 7, I guess. So let's try to do some examples real quick and we'll end it with that. This problem is for the distance between vector B and line through this vector A. The idea of this would be to calculate the projection vector If here, this is your line through A. Let's say this was vector A itself. You have a vector B, which presumably is not going to be on the line, okay? So what we'll do first is we'll calculate the projection vector. So in the picture, that your projection vector will look something like that, okay? Once you get the projection vector, you can calculate the error vector E, which is B minus P. And then we're going to use the error vector to find that shortest distance between B and the line, okay? But let's just calculate the projection vector first. So the way that I will do that is I will go ahead and calculate the projection matrix using this formula, I think is what I'll do. You don't have to do it this way, but I think it'll be good to see. So I'm going to calculate the projection matrix. So we have A times A transpose. Oh, notice that when you're using this formula, the vector is always written as a column. So that's why I wrote A as a column. And then vector transpose will now be a row, okay? Okay. I'm going to divide that by A transpose times A. So the denominator is going to be 4 plus 1 plus 16 plus 9. So that's going to be 30 in the denominator. And then this product is going to give us a 4 by 4 matrix. So we're going to have 2 times 2 is 4. Okay. 2 times 1 is 2. 2 times 4 is 8. And 2 times negative 3 is negative 6. Okay. We're going to do 1 times each of these numbers for the next row. 4 times each of the numbers. And then negative 3 each of these numbers gets us the last row. Okay, I could have chosen some smaller numbers, I guess, but that's okay. So now we have the projection matrix. We will multiply that with vector B to get the projection vector. So I'm going to take the projection matrix that we just calculated. Oh man. Okay, that's annoying. I should just write it out. Okay, so yeah, take the projection matrix that we have. We're going to multiply it with vector B. So we're going to get 1 over 30. It's here 4 plus 4 is 8, minus 8 is 0, minus 6. The next one will be 2 plus 2 is 4, minus 4 is 0, minus 3 is minus 3. 8 plus 8 is 16. I guess that path is minus 0, so minus 12. And I guess let's just check it to be sure. Yeah, the last one will be 9. Okay, that's interesting. So that's going to be your projection vector, but so that's not the answer to the question though, right? So what we're going to do is we're going to calculate the error vector next, which is just b minus p. So b was 1, 2, minus 1, 1. And then the projection vector that we just calculated, it's negative 6 over 30, negative 3 over 30, negative 12 over 30, and 9 over 30. So I'm just going to do that real quick. That's going to be 36 over 30, 63 over 30, negative 18 over 30, and I think that's 21 over 30. If I did my math correctly, that would be it, okay? So that's the error vector. And so the idea here is that in the picture, you can kind of see the length of your error vector is going to represent the shortest distance between B and the line. So the last thing we will do is just calculate the length of E, okay? So maybe let me pull out the 30 real quick. So my numbers are kind of big. I guess I didn't bother checking that when I created this example, but what you would do to get the shortest distance is calculate the length or the magnitude of vector E. So we can leave the 1 over 30 in the front. And then remember to calculate magnitude, you do the square root of x squared plus y squared plus z squared. And then here we have another component, so plus square, okay? So that was supposed to be the idea of this problem. The number is not too important, so I'm going to leave it at that because I don't have a calculator, okay? And I guess I did want to do just one more projection problem, but this will be my last example for the review then, all right? So this time we want to find the vector in the null space of the given matrix that is closest to B, okay? So in other words, what we want is we want to find the projection of B onto the null space of A. So to do that, we first need to find a basis for the null space of A. So I'm going to, so if you want to find the null space, you need to do just a little bit of elimination. I guess in this case, you can see that we actually get a row of zeros when we do that. So we really just have like one equation here. And y and z, we can make those free variables because both the second and the third column are missing a pivot. So what I'll do, I do the usual, assign a parameter to free variables. From there, I can solve for x as r minus 2t. I get the coefficients of r, which are 1, 1, 0. And then I'm going to get the coefficients of t, which are -2, 0, and 1. That's going to give me a basis for the null space of A. Okay. So what we're going to do with those basis vectors is create a new matrix out of them, which I'm going to call B, since A is already in use. Put them into the matrix as columns. Okay. And now we can calculate the projection matrix. Design of the off-diagonal entries, okay? Okay. Now we need to multiply B, then B transpose. So if we do B times B transpose inverse B inverse first. So we have the 1/6 from the inverse. And then here is B. And then here is the rest of the inverse. So I usually am just going to take this constant and just keep it in front so I can avoid working with fractions. So here we get 5 minus 4 is 1. 2 minus 4 is 2. And then 5, 2, 2, 2. Okay. So then I need to take this matrix and we need it to multiply by B transpose on the right now. So B transposed is 1, 1, 0, -2, 0, 1. So I'll finish the calculation here. So our projection matrix. It's going to be 5, 1, -2, 1, 5, 2, and -2, 2, 2. Okay. And then now that we have the projection matrix, I'm looking for the projection of B. So I need to take the projection matrix and multiply with vector B. Okay. That's the projection matrix, and then B, the vector B is 3, 1, 2. So I'm just going to multiply this out, and that will finish the example. And I'll end my review with that. 12 there, I think, and this is 3, 8, 12, and 6. Okay. And so I guess maybe somewhat surprisingly, I got some pretty nice numbers from this. Okay. So then this vector is the projection of B onto the null space of the original matrix A. And that would be the vector that in the null space of A that was closest to B. Okay. All right, I'll go ahead and review with that. Okay. Yeah, so I'll send the recording link to everyone once I've uploaded it to YouTube. I will